Hi everyone, welcome to the class of inferential statistics. This is the continuation of previous class where I already emphasized on the definition of sufficiency and properties of sufficient statistic. Today, we will focus on the topic of completeness and uniqueness. Suppose we have a random sample from the Poisson distribution that has the probability mass function, which can be written as theta to the power x exponential to the power minus theta over x factorial. Given that y1 equals to summation xi is a sufficient statistic for theta, and its probability mass function is given as n theta to the power y1 exponential to the power minus n theta over y1 factorial. Student may ask how we get the probability mass function for y1. Recall that each xi is coming from Poisson distribution with mean theta. Since our y1 is equal to summation xi, we will have expected value of y1 is equal to expected value of summation xi. Using the properties for expected value, we will have expected value of x1, x2, xn. So since each x1 is equal to theta, ex2 is equal to theta, so it will give you n theta. So that's why we will have a probability mass function for y1 is n theta to the power y1 exponential to the power minus n theta over y1 factorial. Let us consider the family G. Suppose that the function uy1 of y1 such that expected value of uy1 is equal to 0 for every theta greater than 0. We shall show that this requires uy1 to be 0 at every point of y1. That is, expected value of uy1 equals to 0. So to make sure that expected value of uy1 equals to 0, it will require that u0, u1, u2, u3 is equal to 0. So since we want to find the expected value, so by definition of expected value, we will have uy1 times the probability mass function. We simplify, we will have this equation. And since exponential to the power minus n theta does not equal to 0, we have shown that u0 and u1 theta n square u2 over 2 theta square we will set equals to 0. However, if such an infinite power series converges to 0 for all theta, then each of the coefficient must equal to 0. That is, u0 is equal to 0 and u1 equal to 0 and square u2 over 2 is equal to 0. Which requires that uy1 equals to 0 except on a set of points that has probability 0 for each probability mass function gy1 theta. Hence, the family gy1 is called as a complete family. Let us refer to the definition of complete family. Let the random variable z of either the continuous type or discrete type have a PDF or PMF that is one member of the family hz theta. If the condition expected value uz is equal to 0 for every theta belong to omega, requires that uz must be 0 except on a set of points that has probability 0 for each hz theta. Then, the family hz theta is called a complete family. Therefore, expected value uz is equal to 0 implies that probability hz is equal to 0 is equals to 1. So using this definition, the only way to make sure that we will have expected value of uz is equal to 0 is by using or by setting the coefficient of uz set equals to 0 except on a set of points that has probability 0 for each hz theta belong to omega. So by the definition, the family hz theta is called a complete family. Let us consider the family of probability density function for exponential distribution. We have 1 over theta exponential to the power minus z theta. We want to show that this family is a complete family. So by writing expected value of uz, so that means we will have uz times the probability density function. So if we want expected value of uz is equals to 0. Since we have exponential distribution does not equals to 0. So that means the only way to make sure the expected value of uz is equal to 0, if we have the coefficient of uz is equals to 0 for all theta greater than 0. Then, by the definition, the family of hz theta is called as a complete family. Let us refer to another example. Let's say we have a normal distribution with parameter mu. Our variance is equals to 1. We want to show that the family of PDF is complete. We need to show that expected value of gx is equals to 0 for all mu belong to any real number. So expected value of gx can be written as integration gx times the probability density function. So we simplify, we factor it out, we have exponential mu square over 2 over square root 2 pi. So we integrate gx exponential negative x square over 2 exponential to the power mu x dx. So the only way to make sure that expected value of gx is equals to 0, since our exponential cannot be 0, so that means the only way to make sure that we have expected value of gx is equal to 0, if by setting the coefficient of gx is equal to 0 for all mu belong to any real number. Hence, by the definition, we will have gx equals to 0 and the family is a complete family. We will have a probability gx is equal to 0 is equals to 1 for all mu belong to any real number. So by the definition, the family of PDF is a complete family. Okay, so that's all. Thank you for listening to my lecture. See you again